PU2 aspirants, so welcome back to the channel, and we know that your midterm exams are ahead, and in this video we are going to solve the most important questions from the chapter coordination compounds. So let me tell you why this video is very important and what are the sources from which I have collected this question. Number one is the model question papers of 2025. So there were 3 model question papers and I have picked all those questions that which were from this chapter. Second is the PU2 2025 final exam board paper. Okay, so from there also I have taken the question so that you can know exactly what type of questions are being asked in the final exams. And third, the most relevant source, that is your PU2 question board bank. Okay, so you can just see that, and I have taken questions from there as well. Okay, so if you watch this video, definitely you are going to solve all the questions from this chapter. So let's get started with the first one. So if you know the pattern, so there will be 2 questions you will get in the MCQ section and 3 questions you will get in the 3 marker section. Okay, so first of all we'll deal with 1 marker questions, or most probably that we call it as a MCQ and FIB. So the first, just a minute. So let's see the first question here. The complex PtCl2 4NH3Br2 is treated with excess of AgNO3 solution. 2 moles of AgBr is precipitated. The primary and the secondary valency of the complex is. Now if 2 moles of AgBr is precipitated, that means these 2 moles of Br will be outside the complex. So what will be the complex formula I will get? PtCl2 NH3 4 and then Br2, right? PtCl2 NH3 whole 4 Br2. Okay, now what is the primary valency? So you want to just calculate the charge of this Pt. So I can calculate, let this be X. Okay, chlorine is -2, NH3 is 0, Br2 is again -2, 0. So that gives X is equal to +4, right? So I can have only one option with that. So that has to be the correct answer. Secondary valency is the coordination number. So you can see 4 NH3 and 2 chlorine. So that is the coordination number 6. So option number C. Next, ambidentate ligand here is. So we know that NO2 is an ambidentate ligand. Sorry, not NO2 plus. Sorry, Cn minus, right? NO2 is not NO2 plus. Yeah, Cn is an ambidentate ligand. You have Cn and Nc both can react, form bond with the metal. Next we'll go to sample question paper 2 of 2025. So the square planar complex of MABXL shows. So it shows 2 cis and 1 trans form. So that is your option number A here. Next, the magnitude of CFSE can be related to the configuration of d orbitals in a coordination entity is. So now let us see, let me tell you, if delta O is less than P, okay, delta O is less than P, that means it is like a weak field ligand configuration, and if delta O is greater than P, then it is a strong field ligand configuration you should think. Okay, so then our question is asking for D4 configuration, basically it is asking. So D4, if delta O is less than P, delta O is less than P means weak field ligand. In that case the configuration will be T2G3 EG1, which is already correct. Now let's see option number B. If delta O is greater than P, then the configuration, this is not, this is, it should have T2G4. And if delta is less than P, it is also incorrect, not this one. And if you have delta O less than P, then T2G4, no. If delta O is greater than P, then it is strong field ligand, you will get T2G4 EZ0. So this is also incorrect. Okay. Now moving to the most expected questions that I have taken from question board bank. So purple compound M has a formula CONH3 whole 6 Cl3 on adding excess of AgNO3. 1 mole of M produces 2 moles of AgCl. Okay. So if the secondary valency of cobalt is 6, then correct formula of the complex is. Now see, 2 moles of Cl is there. 2 moles of Cl should be precipitated. That means 2 Cl should be outside. So I should have like this. NH3 whole 6 and then okay 6 NH3 and okay, then you have here, see, we can have only, the structure should be like this, CONH3 whole 5 Cl and then you have Cl2 and you have NH3. That should be the structure, because we can have only 2 Cl outside, okay, here, and the coordination number should also not be more than 6. So here if you see the coordination number is 9, which is again incorrect, right? Next, if you see here, coordination number is 6, but there are 3 chlorine outside, so this is also incorrect. Here if you see coordination number is 7, so that is incorrect. Here you can see coordination number 6 is there, correct. 2 chlorine is outside, that is also correct, and 1 ammonia is there, so option number C here. Next, question number 2, let's see, which among the following is not a double salt? So these all are double salt. Potassium ferrocyanide is a complex, okay. From examples you can solve it. Next, the correct order of stoichiometries of AgCl formed when AgNO3 in excess is treated with complexes. Okay, so when you treat it with first complex, okay, coordination number valency is 6, so 6 NH3. So for the first one I can write the formula like this, right? This can be the formula of the compound. Now if you see 3 chlorines are present outside, so 3 chlorine will be precipitated, so the number of moles will be 3 AgCl. Then you have 5, and if you see this one, in that also what I can write, I have 5 NH3 and I should have 1 chlorine, so that the coordination number remains 6, then it will have 2 Cl outside. Next we have CO NH3 whole 4 Cl2, right, and then 1 chlorine should be outside. So now this one will give me what? Number of moles present here is 3, number of moles of AgCl produced is 2, number of moles of AgCl produced is 1, okay. So 3, 2 and 1, that is option number B here. Next, moving to question number 4, which among the following has the highest molar conductivity? So if you see next option number A here, it has 4 K ions and 1 this complex ion, right? So total 5 ions are produced. Next we have this one 3 and this one 1 4 complex, so 4 ions will be produced. Next we have 2 complex ions here, and next we have 1 complex ion, so 1 ion will be produced. So we will have here 5 ions, so that is why option number A is the correct answer. Next, the primary and the secondary valencies of the following complexes are. So if I have this complex Fe C2O4 3 minus, okay. So first let us calculate the oxidation number here, let it be X, this is minus 2 C2O4, 3 C2O4 is there, so it will become minus 6, that is equal to minus 3, so X will become plus 3, right. And what is the coordination number? So you do not think 3 here, because C2O4 is a bidentate ligand. So if it is a bidentate ligand, that means what? Each C2O4 will form 2 bonds. So 3 C2O4 will form 6 bonds, right? So that is why the secondary valency will be 6. So option will be option number B is the correct one. Next, moving to question number 6 here. The coordination number of the central atom or ion is determined by only by the number of pi bonds? No, it is determined by sigma bonds, okay. Both by the number of sigma and pi bonds? No. Only by the number of sigma bonds formed by the ligand with the central atom? Yes. By the total number of electrons present in the ligand? No, okay. So by only by the sigma bonds we can determine the number of or the coordination number of the metal. Next, the correct IUPAC name of the given compound. So first of all, it has to be potassium, right? First the cation is written, so potassium, 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 potassium. It is correct in all, okay. Next we have trioxalato, okay. Trioxalato should be there. Trioxalato, trioxalato. Here we have trisoxalato is not required. Here only oxalato is there, so these two are wrong. Next we have chromium. Since it is a part of negative ion, chromium should be chromate, okay, and then we should have 3. So option number B is the correct answer here. Next we will see can show which type of isomerism. So if you see it is having Cl2 and Br2, so definitely it can show you that is called as ionization isomerism, and since it is a coordination number 6, you will also get geometrical isomerism, right. So ionization plus geometrical, option number B here. Next, possible isomerism in the given complex. So if you see here, this particular compound, okay, since this is there, it can show you NO2 is there in both the complexes, so it is an ambidentate ligand. So what we can get, first of all, we'll definitely get linkage isomerism, right? Linkage isomerism, I can eliminate these two. Now this is of the type MA3B3, so it will show geometrical isomerism, so we'll also get geometrical isomerism, option number D here. Next, in the reaction COCl2 NH3 4 plus Cl minus, we get this compound, two isomers of the product are obtained. So always remember, in such cases the first product is always cis. Okay, so option number A here. Next, which type of complexes shows geometrical isomerism? So we know that we have tetrahedral will not show, square planar will show. Here all the ligands are same, so that will also not show, and again tetrahedral will not show. So option number C here. Next question, which type of complexes does not show geometrical isomerism? Does not show. Okay, so here if I see for not showing, tetrahedral, okay, MX2L2 tetrahedral will not show, others all of them will show. So option number A. Next, the optical active complexes. So you remember, optical activity is always for cis form. Okay, trans form will not show, cis form will show. So option number B here. Next, linkage isomerism arises in a coordination compound which contains ambidentate ligand, option number A. Next, the type of isomerism arises from the interchange of ligands between the cationic and anionic entities of different metal atoms present in a complex is called as coordination isomerism. So here what happens, suppose you have metal 1 and ligand, and you have another metal and ligand. So what happens, this is M1, this is M2. So the ligands can get exchanged here. Okay, that is called as coordination isomerism. Next, the inner orbital complex is, so always remember, generally, okay, not always, but inner orbital complex is generally formed by strong field ligand, and outer orbital complex is always formed by weak field ligand. This is for coordination number 6. Okay, and inner orbital means the hybridization should be D2sp3, and outer orbital means the hybridization should be sp3d2. So now let's directly check. So here you can see weak field ligand, weak field ligand, weak field ligand. We can directly say option number A, but before going that, let's check it. Okay, CONH3, this example is already there in the book, and if you remember, it has D2sp3 configuration. So why do we call it inner orbital complex? Because here 3d orbitals are used, the inner d orbital. Here what happens, the 4d orbitals are used, the outer d orbital. Okay, so option number A here. Next, the high spin complex is, so high spin complex is also, here also remember, high spin complex means it should have unpaired electrons. Okay, and that also is generally formed when we have weak field ligand. And low spin complex means it should have paired electrons. Okay, or I can say no unpaired electrons. Okay, in that case we'll get a, in case of strong field ligand, right? So now if I see that COF6 is a weak field ligand, other all are strong field ligand, so in that case I'll get a high spin complex. So option number D is the correct answer. Okay, sorry. Next one, let's see here, question number 18. The tetrahedral complex is, so tetrahedral and square planar, how will you remember? Tetrahedral and square planar. Tetrahedral will have sp3 hybridization, square planar will have dsp2 hybridization. Again, tetrahedral is generally with weak field ligands, and square planar is generally with strong field ligand. I am always using the word generally, okay, so it is not mandatory, but yes, you should always check once before you are selecting the option. But here we have already seen this option is there in our book, NCERT book, this option is there, and it has a hybridization of sp3. Okay, moving to the 19th question, the square planar complex is, so NiCN4, we have seen this one in the example, NiCN4 is the square planar complex. Next, we have the complex with maximum magnetic moment is, again, when I have maximum magnetic moment, okay, maximum magnetic moment if the question is asking, that means what? magnetic moment depends on number of unpaired electrons, right? Depends on number of unpaired electrons. If number of unpaired electrons are more, magnetic moment will be more. Now number of unpaired electrons will be more in which case? In case of if I have a weak field ligand. Okay, in case of weak field ligand, there will be less number of unpaired electrons and maximum magnetic moment. So here I can find weak field ligand in place of fluorine only. So option number C is the correct answer. Next we have the incorrect statement about the valence bond theory. It involves a lot of assumptions. That is a correct statement. It gives a quantitative interpretation of magnetic data. No, it does not give. Okay, that is the limitation. Then it does not explain the color exhibited by the coordination compounds. Yes, it could not explain. It gives a quantitative interpretation of the thermodynamic. No, it does not give. So what are the incorrect statement? 2 and 4. That is option number C here. Next, question number 22. The crystal field theory is an electrostatic model which considers the metal ligand bond to be ionic. Yes, that is correct. The crystal field theory considers ligand as point dipoles in case of neutral molecules. Okay, it considers them as point dipoles. So identify the correct statement here. Both the statement are correct. So that is why option number A is the correct answer. Next, moving to question number 23. The degeneracy of d orbitals is of the isolated gaseous metals is maintained when? The degeneracy of the d orbitals of isolated gaseous metal is maintained when? Okay, negative charges of a dipole molecule surround the central metal atom. Spherically symmetrical field of negative charges surround the metal. Spherically unsymmetrical field of negative charges surround the metal. Non-spherical unsymmetrical field of negative charges surround the metal. So it is because spherically symmetrical field of negative charges surrounds the metal. Okay. Moving to the next question number 24. In a complex with secondary valency 6, the set of d orbitals which experience more repulsion with electrons of the ligands are. More maximum repulsion, where do we observe? We find maximum repulsion when we have this these two orbitals dx square minus y square and dz square, because they are along the axis, right? So they face maximum repulsion. So that is why option number A. Next we have, according to the spectrochemical series, the strongest field ligand. This is direct from the order, you can see it is option number A, CO, carbon monoxide. Next we have the correct electronic configuration for D4 in a weak, so it's not carbon monoxide, sorry, carbonyl ligand. Okay, so in a weak field ligand is D4 in a weak field ligand. In a weak field ligand, what happens? Splitting is less, right? And okay, splitting is less means what? 1, 2, 3. The electron can directly go to the higher level. So we will get T2G3EG1. Okay, that is option number A here. Next, the relation between the crystal field splitting energy of octahedral and tetrahedral complexes are. So tetrahedral is actually 4/9 of octahedral. Okay, that is option number A here. Next, question number 28. The shape of pentacarbonyl iron is. So if I have pentacarbonyl iron, okay, the shape of pentacarbonyl iron, this one is called as trigonal bipyramidal, which is option number C. Next we have the number of bridge carbons in CO in octacarbonyl dicobalt. So if you see the structure, it is like this. We have like this the ligands, right? Okay. So now what happens if you see 8 we have. So what is the number of bridge carbons? We have 2 bridge carbons, that is option number A here. Now last question for MCQs. In black and white photography, what is used? The hypoform is AgS2O3 okay, so that is your option number A. Now I'll move towards the fill in the blanks questions. Okay, I hope this is visible. This I have taken directly from the question bank, so you can solve it. The number of groups bound directly to the metal is its secondary valency, right? The coordination number. The dash valencies are normally ionizable, primary valencies are ionizable. The spatial arrangements are called coordination polyhedra. Next, dash dissociate into simple ions completely when dissolved in water, potash alum. Next, in a coordination entity, the central atoms or ions are referred as Lewis acids. Why? Because they accept electrons. Next set 2, let's see. We have when a ligand uses its 2 or more donor atoms simultaneously to bind a single metal atom, then it is a ambident, 2 or more donor atoms simultaneously, then it is a chelating ligand. Simultaneously means it is chelating ligand. Ligands which has 2 different donor atoms and either of the 2 ligates to the metal is called. So at a time only one donor site is binding, then it is ambidentate ligand. Next, the coordination number of the central atom is determined by the number of sigma bonds formed by the ligand with the central atom, right? Coordination number of the central atom is determined by the number of sigma bonds that is formed. Dash complexes do not show geometrical isomerism. We have homoleptic complex because you need to have different ligands, but if it is same ligand then there will be no geometrical isomerism. Facial and meridional isomerism is shown by octahedral complexes, right? Because M8 you can see 6 ligands are there, so it is octahedral complex. Now moving to the set 3 here. Example for polydentate ligand is EDTA. Okay, it is a hexadentate ligand. In a coordination entity like this, dash isomer shows the optical activity. So we know cis isomer shows the optical activity. Next, linkage isomerism arises in a coordination compound containing ambidentate ligand. Okay, dash theory fails to explain the bonds in coordination compounds have directional properties. The Werner theory, okay, that is your Werner theory. Number 4, dash theory fails to explain the bonds in coordination compounds have directional properties, that is your Werner's theory. Okay. Next, sp3d hybrid orbitals have trigonal bipyramidal shape. Option number 5. Okay, this one will be the answer. Next, set 4, CONH3 whole 6 3 plus forms a dash octahedral complex. Okay, so NH3 whole 6, so what all options we have? Okay, this is a strong field ligand, so we will get diamagnetic, so that is why option number 1. NiCl4 2 plus is a dash complex. So if you see, it is a high spin complex because it is a weak field ligand. Okay. Next, dash is an inner orbital complex. So this one will be an inner orbital complex because I have a strong field ligand. The oxidation state of nickel in this compound is 0. So that is option number 4. The hybridization of NiCN4 2 minus is, since it is a strong field ligand, so the hybridization is DsP2. Next set 5, let's see, dash ion can bind through 2 nitrogen and 4 oxygen atoms to a central metal atom. Dash ion can bind through 2 nitrogen and 4 oxygen, that is your ethylene diamine tetraacetate, EDTA. Okay. NiCO4 complex is dash and diamagnetic, so it is tetrahedral actually, okay, and diamagnetic, so option number 2. Next, we have FeF6 3 minus has a paramagnetic moment of dash unpaired electron. So let's calculate this one. FeF6. Okay, FeF6 means in that if I have FeF6 3 minus, in that what is the oxidation state of Fe? It is +3, right? +3 means 3d5 configuration, and this is a weak field ligand. Okay, so there will be no pairing of electrons, so it has 5 unpaired electrons, so option here will be 5. Okay, next, MnCl6 3 minus is outer orbital, Mn, it is a weak field ligand, so it will definitely be paramagnetic. So what? Outer orbital paramagnetic complex. According to spectrochemical series, iodide ion is a weak ligand. Okay. Now we have one more set, the last set in case of fill in the blanks. So let's see here. In high spin complex, D4 has T2G3 Eg1 configuration. In crystal field splitting, the subscript G is not used for tetrahedral complexes. We only use T2 and E in that case. If a complex having D1 electron absorbs light with energy in blue-green region, then the complex appears to be violet. Okay, this example is there in TiH2O whole 6. That example color is asked as a question. The dash theory attributes the color of the coordination compounds to d-d transition of the electron. That is your crystal field theory gives you this knowledge. The removal of water from this one on heating gives you a colorless compound, because when we heat it, when the ligands evaporate or when water evaporates, all the d orbitals become degenerate, and now the electrons cannot undergo d-d transition, right? So that is why. So we have this one as 5. So now let's see the 2 and 3 marker questions from this chapter. Okay, so first I'll take some questions that were asked in the sample question papers of 2025. So this is the question paper, sample paper 1 of 2025, and there was no 2 marker question in this paper for this chapter. There was a 3 marker question. The question goes like this, that for the complex mercury tetrathiocyanato S cobaltate 3, find the following. You have to find the coordination number of CO, identify the ligand present in this complex, and does ionization isomer exist here or not. So you can already see the answer, but before answering this, or to be able to answer this, we need to know the structure of the compound. So first what I have, mercury, right? Mercury Hg. There is +1 charge of mercury, and you have tetrathiocyanato S cobaltate. So I'll draw like this. First I should write the metal, cobalt, tetrathiocyanato, that means SCN4, right? Tetrathiocyanato S cobaltate 3. So here if you see, cobalt charge is +3, okay, and SCN charge is -1. So what is the total charge of this complex? 3 minus 4 is equal to -1. Okay, so that means this charge is -1. Now what will happen if you crisscross? We will get the compound like this, HgCO SCN4. Okay, this will be the compound. So now what we have to find out, coordination number of cobalt. So you can see that 4 ligands are bonding here, so the coordination number will be 4 here. Which is the ligand present? SCN minus, so that is why SCN minus here. Does ionization isomer exist? So ionization isomer will exist if there is one auxiliary ion present which can be replaced here, but we cannot replace metal and metal, so no auxiliary no ionization isomer exists here. Okay. Next, define crystal field splitting. Sketch the energy level diagram for this crystal field splitting of d orbital in the tetrahedral complex. Okay, so it is asking for tetrahedral complex. So first of all, if you remember, what is crystal field splitting? So crystal field splitting is an electrostatic model which considers the metal ligand bond to be ionic, arising purely from the electrostatic interactions between the metal ion and the ligand. Okay, so that is what you have to explain, what is a crystal field splitting. Okay, next, ligands are treated as point charges in case of anion or point dipoles in case of neutral molecules. Now they have asked you to draw a diagram to show the splitting in tetrahedral field. So first what will happen? You will have 5 degenerate orbitals. Now what will happen? The energy will go higher. Okay, once the ligands appear, there will be, the energy level will go higher, and after that there will be splitting. Okay, so splitting will be like this. Here there will be 2 orbitals and here there will be 3 orbitals. So you have T2, one second, yeah, here T2 and here E. Okay, so this is the splitting of tetrahedral in crystal field theory. Okay, next, moving to what is the significance of synergic effect in metal carbonyls? How many bridged and non-bridged carbonyl compounds are present in octacarbonyl dicobalt complex compound? So first of all, what is the significance? The significance is it strengthens the metal CO bond. Okay. Next, how many bridge and non-bridge is there? So this is the structure of the compound that is asking you, octacarbonyl dicobalt complex. Okay, so here we can see 2 bridge carbonyls are there and 6 non-bridge carbonyls are there. So 2 bridge and 6 non-bridged. Okay, Next, moving to sample question paper 2 of 2025. Now let's come to sample question paper 2 of 2025. There is a 3 marker question, this one. Write the IUPAC name of the given compound and draw its geometrical isomers for the complex. Okay, so if you see IUPAC name, if I want to write, so first of all I'll write the ligand name, alphabetical order. So this ligand name is ethane 1,2-diamine, and we have to use the word bis for this. So bis ethane 1,2-diamine, then dichlorocobalt. And what is the oxidation state of cobalt here? So let it be X. Okay, chlorine is -2, this is 0, is equal to +1. So we will get here 3, right? So I have, this one will come as 3. Okay, cobalt 3. Yes, next we have the geometrical isomers for this complex. So you will have cis and trans. So this is the one where chlorine are in opposite side, this is the trans, and where chlorine are close to each other, this is cis. Okay, next we will move to again sample question paper 2 only. There is one more question. Write any 3 limitations of valence bond theory. So I have given you here 6 points. You can write any 3 here. So first one is, it involves a lot of assumption, does not give quantitative interpretation of magnetic data, does not explain the color exhibited by the coordination compounds, does not give quantitative interpretation of the thermodynamic or kinetic stability of the coordination compounds, does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordination complex. So it cannot explain why certain coordination number 4 complexes are square planar whereas certain are tetrahedral. What is the explanation for that? That is also not given by valence bond theory, and it does not distinguish between weak and strong fields. So you can write down any 3 from here. Okay, next question will come to sample question paper 3 of 2025. The question was, okay, this was a first I have taken this MCQ question. Okay, no, not MCQ. Each using abbreviations of the following ligands, identify the number of donor sites and write the formula of each ligand. Okay, so first one is En. En, if I just write down the structure, it is like this: CH2, CH2, then you have N, then you have C double bond O minus, C double bond O minus. Similarly here you have N, and here you have C double bond O minus and C double bond O minus. So this is the complete structure, and if you see the number of donor sites, here we have 6 number of donor sites: 1, 2, 3, 4, 5 and 6. Okay, now coming to option question number B, you have, okay, sorry, just a minute, I did a mistake here. This is B. Okay, EDTA is B. This is B. Okay, now let me draw here for N, A. A is En. En structure is like this: CH2, NH2. Then I have an eraser. I can have here CH2 and NH2. Okay, so here also 2 ligands, here also 2 ligands are there. So total you have number of donor site here is 2. Okay, En. Then we have C, P, PH3. So we have P, you have PH, PH and PH structure. Here this is the donor site. So number of donor site is only 1 here. Okay. Now we will have next question: using valence bond theory, explain the geometry, hybridization and magnetic property of COF6 3 minus ion. Okay. So first of all, if I write COF6 3 minus, okay, what is the oxidation state of cobalt here? +3. Okay, so what is its electronic configuration? Normal cobalt is 3d7 4s2. So this one will be 3d6. Okay, how can I draw it? If you have like this 1 2 3 4 5, 1 2 3 4 5 and 6. Okay, this is 3d6 configuration. Now what we can do, you need that there are 6 ligands, right? I need 6 empty orbitals. So here you can write fluorine minus is a weak field ligand, so pairing of electron does not take place. Pairing of electrons does not take place. Okay, this you have to mention. So next what I will be having, for the orbitals, cobalt 3 plus, what are the orbital available? We have 3d6, okay, I have, so you have 1, 2, 3, 4, 5 and 6, 3d6, 4s, then I have 4p, okay, and then I have 4d. Okay, so now what happens, these the orbitals which are present here, sp3d2, we need 6 orbitals, right? So this sp3d2 undergo hybridization, okay, and once they undergo hybridization we get 6 new hybrid orbitals, that is 1, 2, 3, 4, 5 and 6. Okay, and these hybrid orbitals, in these hybrid orbitals what happens, fluorine donates the electrons. You have to just denote like this, okay, and what are these? These are sp3d2 hybrid orbitals. Okay, now what are the questions that is asked? The question is asked about the geometry. So what will be the geometry here? The geometry will definitely be octahedral. Always remember, whenever there is coordination number 6, the geometry will always be octahedral. Next we have hybridization. So hybridization we have already found out, it is sp3d2. And next we have magnetic property. So you can see here in cobalt there is unpaired electrons, right? So if there is unpaired electrons, then the magnetic property will be paramagnetic. Okay, paramagnetic we will get here. Now moving to the next one, question number 29, give any 3 applications of coordination compounds. Here I have given 4 applications, you can write any 3. Hardness of water is there, extraction process is there, purification of metals is there, and these compounds also contain the daily life compounds which we use, they are also coordination compounds. Okay. Next, we'll go to actual PU2 2025 final paper questions. So here are some, first of all, I'll take some MCQs that is there. Which of the following is not a subdivision of structural isomerism? So we know that geometrical isomerism is not a structural isomerism. The structure of pentacarbonyl iron 5 is there. The structure of that compound is like this. Okay, pentacarbonyl iron, and this is called as trigonal bipyramidal, and we write it as like this, trigonal bipyramidal. Okay, next, state any 3 postulates of Werner's theory. This is very important and common question, every year you can expect this question. So the first assumption or the first postulate is, it has the coordination complex have 2 types of valencies, primary valency and secondary valency. Now the primary valencies are normally ionizable and are satisfied by negative ions. What are secondary valencies? Secondary valencies are non-ionizable, they are satisfied by neutral and negative ions, and the secondary valence is equal to the coordination number and is fixed for a metal. Okay. Next, the ions or groups bound by the secondary linkages to the metals have characteristic spatial arrangement corresponding to the different coordination numbers. Okay, so you can write this first 2 points. The first point is that the coordination complex have 2 types of valencies. The second point is about primary valency, and the third point you have to write is about secondary valency. Okay. Next, this is a question again from PU2 2025, question number 28. CONH3 whole 5 BrSO4 is an octahedral coordination compound. Write its IUPAC name and draw the diagram which indicates the splitting of d orbital in the above complex with respect to CFT. Okay, so first of all we'll write the IUPAC name here. So I have this compound, that is CONH3 whole 5, okay, and BrSO4. Right. So if I want to write the name of this compound, what I can say is, you have to write alphabetical order. First is amine, then is bromine. So I will write penta, okay, then amine, okay, then I have bromo, then I have write the metal name, that is cobalt, and in the bracket I have to write its oxidation number. So let's calculate the oxidation number. This is X, this is 0 because it is a neutral ligand, this is minus, and this is sulfate is -2. Again the whole complex is neutral, so 0 means the total charge of this compound is 0. So X gives me +3. So cobalt +3 sulfate. Okay, I'll get here sulfate, so that is the final name of this compound. Next is you have to draw a diagram to show the splitting. So it shows a I'll say coordination number 6 octahedral splitting. So how do the octahedral splitting is there? T2G is there at the down and EG is there at the top. We have to show this diagram. Moving to the next one, what are the facial and meridional isomeric structures of this compound? Mention the coordination number of the metal ion in the above complex. So facial and meridional, you have remembered, you can draw it like this. So just a minute. Yeah. So facial, you can see 3 NO2 groups will be there at this point on one side and NH3 on another side, and in meridional 3 NO2 group will be present in one plane. Okay, and what is the coordination number? You can see there is 3 NH3 and 3 NO2, so total the coordination number is 6 here. Okay. Next, we'll go to some most expected questions that were not asked in the previous years, but we can expect in this year. So first of all, these are 2-marker question. Give the difference between double salt and a complex. Okay, so double salts are something which dissociate completely in water. You can give example. Carnallite is there, KCl MgCl2.6 H2O. You have more salt FeSO4.NH4 2SO4.6 H2O. You have potass alum. So these are all double salts. Now what is a complex? Complex do not dissociate completely. Example, FeCN6 4- K4FeCN6. Okay. Next question, what is meant by double salt? Give an example. Same thing, double salt are something which dissociate into simple ions completely when dissolved in water. Here again the same examples I have given. Next is FeSO4 solution mixed with ammonium sulfate solution is 1:1 molar ratio gives the test for Fe2+ ion. But copper sulfate solution mixed with aqueous ammonia in 1:4 ratio does not give the test of copper 2+ ion. Explain why. Very good question. Okay, good question this one. So the question is saying that if you take FeSO4, okay, and you mix it with ammonium sulfate, okay, then whatever product is formed, this product gives the test for Fe2+. Okay, but if you take copper sulfate and you mix it with 4 times of ammonia, so whatever product we get, that does not give the test for copper 2+. Okay, so that is the question here. So now what do we understand here? If it is giving the test for Fe2+, that means Fe2+ ions must be produced in this product. So this must be a double salt. Here copper 2+ ions are not produced, so this must be a complex ion. So that we can show or can write in this way. FeSO4 solution mixed with NH4 whole to SO4 in 1:1 molar ratio forms a double salt. Okay, that is FeSO4.NH4 whole to SO4.6 H2O, which is called as Moore salt, which ionizes in the solution to give you Fe2+ ion. Now when you dissolve this one, you will get Fe2+ ion in the solution. Hence it gives the test for Fe2+ ions. That is why, because you are getting Fe2+ ions, it gives the test for Fe2+ ions. Next, copper sulfate solution mixed with NH4 whole to SO4 solution in 1:4 molar ratio, right? This is 1:4 molar ratio, forms a complex. The complex formed is this one, CuNH3 whole 4 SO4. This is a complex formed here. Now the complex will not give you Cu2+ ion, does not ionize to give you Cu2+ ion. Hence it is not give the test of Cu2+ ion, because the second one forms a complex. There is no free Cu2+ ions, so you cannot give the test of, you cannot get the test of copper 2+ ions. Okay. Next one, what is chelat ligand? Give an example. So when you have di or polydentate ligands, okay, when they form with bond with metal. So if you have a metal and you have a like a didentate ligand, or I can say a polydentate ligand. Okay, so these type of polydentate ligand, they form a cyclic structure with the metal, and that is called as chelating ligand. So when a di or a polydentate ligand uses its two or more donor atoms simultaneously to bind with a single metal ion, it is called as a chelate ligand. Example, you can have ethane 1,2-diamine or oxalate also. Next, name the metal present in hemoglobin and vitamin B12. Hemoglobin is iron, vitamin B12 is cobalt. Next, if secondary valency of CO3 plus is 6, then the number of moles of AgCl formed when excess of AgNO3 is added. Okay, so now when you need to know that cobalt is having 6 valency, so a 6 coordination number, so it will form 6 bonds here. So what can be the product here? CO NH3 whole 6. Okay, and the Cl3 extra will be present outside. So now when I react this one with AgNO3, okay, you will get all this chlorine which is present outside will react to give you AgCl. So how much AgCl moles I will get? 3 moles of AgCl I will get. First one I will get 3 moles. Okay, now coming to the second one, you have again there is CO, I need NH3 whole 5 is there. Okay, and I can take 1 chlorine from here because I have to maintain 6 coordination number here. So how many chlorine is remaining outside? We have 5 plus 3 8 6. Okay, so here we have 2 chlorine outside, so this one will give me 2 moles of AgCl. Okay, that is 2. Okay, clear? Now moving to the 7th question, what are primary and secondary valencies of a complex with molecular formula PdCl2.4NH3 if it precipitates 2 moles of AgCl per mole of compound with excess of AgNO3. If you are getting 2 moles of AgCl, that means 2 chlorine will be outside. So if 2 chlorine will be outside, what will be the formula of the compound? I will keep 2 chlorine outside, it will be, right, this is the formula of the compound. Now you have to then what is the primary valency, means what is the charge of palladium here. So X plus 0 minus 2 is equal to 0, that gives X is equal to plus 2, right. So what is the primary valency? That is plus 2. Next question is asking you secondary valency, means what is the coordination number here? It is 4. That is because 4 bonds are formed, so coordination number is 4. So option number answer of the B will be 4 here. Okay, next write the correct IUPAC name for the following. So let's write down the IUPAC name here. So first of all, amine and aqua. Amine will come first alphabetically. Okay, so I have to write here triamine. Okay, next triaqua. Okay, ligands are over, then metal is chromium. Here I have to write the oxidation number. So for oxidation number, let chromium be X, NH3 charge is 0, H2O charge is 0, chlorine is minus 3, like minus 1, 3 chlorines will be minus 3. So that will give me plus 3, right. Then I have chloride here. Now coming to option number or second one, COSCN4. Okay, so you can write here, this is thiocyanato S. So tetra thiocyanato S. S indicates that S is forming bond here. Cobalt is there. Okay. Okay, here I have missed one, this is minus is there. Okay, so since it is a negative ion, this one will be cobaltate. Okay, now if you see X and SN is minus 1, so there is minus 4 is equal to minus 1, that gives me X is equal to plus 3. Okay, tetrathiocyanato S cobaltate 3. Now coming to the next one, draw the structure of geometrical isomer of this particular compound CONH3 whole 4 Cl2. So you can draw cis. If chlorine are opposite, that is trans. When chlorine are adjacent, that is cis. So we can draw cis and trans isomer. Next, among tetrahedral and square planar complex, which will not show geometrical isomerism and why? So tetrahedral is something which will not show geometrical isomerism, and the reason for that is Tetrahedral complexes do not show geometrical isomerism because in tetrahedral arrangement, the relative position of all the 4 ligands are equivalent and identical with respect to each other. Okay, so the all the 4 ligands are equivalent in direction and position, so there is no isomer existing there. Now we will move to 3-marker question. Using crystal field theory, explain the color of TiH2O whole 6 3+. So you have to write it in points. Okay, so first of all, TiH2O whole 6 is an octahedral complex where the so Ti3+ has D1 electron. Okay, only D1 is there. Why? Because if you see titanium, okay, what is the electronic configuration? 3d2 4s2. Now Ti3+, okay, in this complex H2O is neutral ligand, so titanium charge is +3. It will be 3d1, right? So the single electron in the metal d orbital is in T2g level. Since it is a octahedral complex, the splitting will be like this. This is T2g and this is Eg. There is 1 electron present at the bottom. Okay. Next, the next higher state available for the electron is the empty Eg orbital. This is the next higher orbital level available. Now, if the light corresponding to the energy of blue-green region is absorbed by the complex, it would excite the electron from T2g to Eg level. So, to excite, this gap is such that blue-green, the frequency of blue-green light is the correct frequency for this electron to absorb and to get excited. So when it absorb this blue-green light and gets excited and then comes out, it emits light of violet color. Okay, so that is why the complex appears to be violet in color. Okay. Next, we have illustrate the influence of ligand on the color in NiH2O whole 6 2+ complex. This is also a good question. So if you see NiH2O whole 6, H2O is a weak ligand. Okay, so earlier it was green color. Now when you add En to that, 1 En will form 2 bonds. So what will happen? 2 H2O will go out and 1 En will replace. So you can see 2 H2O has gone, 1 En has come. Now if you are adding another molecule of En, another 2 molecule will go. So now we will have just 2 H2O and 2 En. Now again you are adding, so that all the H2O will be removed and you are having only NiEn. So how the color has changed from green to pale blue, then blue purple and then violet. Yeah, you have to write this equation only in this question. Next, how many square pyramidal units are present in decacarbonyl manganese? Write the formula and structure. So if you see, this is the formula Mn2CO10. The structure is like this. So the question is asking how many square pyramidal units. So this is 1 square pyramidal unit and this is another square pyramidal unit. So we have 2 square pyramidal units. Next, with the help of structure, explain the synergic effect in metal carbonyls, how it affects on MCO bond strength in such compounds. So synergic effect, when you have to explain, you have to draw this diagram every time and you have to explain the bond formation. So where exactly the sigma bond is forming and how the pi bond is forming, that you have to explain. So in sigma bond, what happens? The metal, first of all, the metal carbon bond has both S and P character. The sigma bond, the MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into the vacant orbital of the metal. So you can see here, for the sigma bond, the electrons present in the carbonyl is donated in the vacant orbital of metal. Now metal will also form bond, metal will also donate electron. So the filled d orbital of the metal, okay, from where the electron pi bond is formed, the pi bond is formed by the donation of a pair of electrons from a filled d orbital, okay, of metal into the vacant anti-bonding pi orbital of the carbon monoxide. Okay, into the vacant orbital it will donate electrons. It strengthens the bond between CO and the metal. So what is the significance? It strengthens the bonds. Now coming to the next one, explain with 2 examples each of the following: coordination polyhedron, homoleptic and heteroleptic. So just example you can give. What is coordination polyhedron? It refers to the spatial arrangement of the ligands around the central atom in a coordination complex. Okay, spatial arrangement of ligands around the central atom in a coordination complex. Example is NiCO4. Next, what is homoleptic? Homoleptic is one where you have all the same type of ligands. Okay, example is NiCO4. What is heteroleptic? When you have a combination of different types of ligands are present, is a complex in which the central metal atom is coordinated to different types of ligands. You have an example like this. Okay. Next, we have some question on the basis of what I'll say, that is isomerism. You have to draw the cis and trans isomer for each of them. So ML4X2 is there, right? ML4X2. So first, if I draw the I have X like this, L is like this. Okay, so this is the trans form, and cis form I can just have like this, where I can draw 2X like this, and then I have L. Okay, so this is trans form and this is cis form. Now you have MLL whole to X2. Okay, now we have MLL whole 2 and X2. Okay, so now we have M here, X is there, and then you have LL. Okay, this is the trans form, and then we have cis form. How we can draw the cis form? I can just, okay, so it is something like this. Okay, this is the cis one, this is the trans form. Now you have ML3X3. So here we have facial and meridional. Okay, so I can just draw like this. So if I have just all the three in one side and another three in one side, this is facial. And if I want to draw meridional, it will be L, L, L and X, X, X. So this is meridional. Okay, so these are the isomer structures. Next, the same thing. Yeah, draw the optical isomers of the given compound. PTCl2En2 and COEN whole 3. Okay, so now what you have to draw here, optical isomers. Okay, so first one, you have PTCl2En2, right? So if you know, this is of the type what? MLL whole 2 A2, right? This type. And here I have told you, in this type the cis one will be optically active. So what will be the cis form of this one? I can draw like this, PTClCl En. Okay, now if you draw the mirror image of this one, I'll get PTClCl, then I have like this En and En. Okay, next we have second one, COEN whole 3. Okay, so CO we have like this, En I'm just drawing like this. This is COEN whole 3 and its mirror image if you draw. Okay, so that will be the structure. Next, coming to this one, out of the following two coordination entities, which is chiral? Okay, so chiral one is always, the cis one will be chiral undoubtedly, trans one is optically inactive, so I can correct this one. Cis one will be optically active. Next, explain linkage isomerism with example. So linkage isomerism arises when you have an ambidentate ligand. You can just give one example, this one, and what will be its linkage isomerism? So you have ONO. Okay, so that is your linkage isomerism. Next we have ionization isomerism. So this form of isomerism arises when the counter ion in a complex salt is itself a potential ligand and can displace a ligand from which then become the counter ion. So what happens, you can see what is saying, the counter ion, this is the counter ion. It itself is a potential ligand and can displace a ligand which can then become the counter ion. So this Br can displace SO4 and SO4 will become the counter ion. Okay, so that is the ionization isomerism. Next we have solvation or hydration isomerism. So solvent isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. Okay, so whether it is bonded to the metal directly or not. So here we have 6 water molecules that is there, and if this water molecules comes out, one of the water molecules comes out, this is another variant, or this is the isomer, hydrated isomer of this particular compound. Next we have coordination isomerism. So this type of isomerism arises from the interchange of the ligands between the cationic and anionic entities of the different metal ions present in a complex. Okay, so there will be exchange of NH3 and CN. Here will be there is exchange. So when you exchange the ligands between two coordination entities, we call it as a coordination isomerism. Next, explain the hybridization property, magnetic property and geometry of CONH3 whole 6 3+. So I have already discussed for COF6 3-. Similarly, you also have for CONH3 whole 6 3+. Okay, so first step is to write the oxidation state of cobalt and its electronic configuration. So what is this electronic configuration? 3d6. You need to draw that. Right. Next, what is there? You know NH3 is a strong field ligand. So what will happen? Pairing of electron takes place. Okay. So if there is pairing of electrons takes place, we have to pair it in such a way that I need 6 vacant orbital for the NH3 to donate the electron. So you have like this CO, I can write like this 3D, and then I have 4s and I have 4p, right? So I'll draw 3D like this, 3d6. So pairing of electrons takes place. So I'll have 2 unpaired electron, then you have 4s and then we have 4p. Okay, so we have D2sp3. D2sp3 is the hybridization of these orbitals. So what will I get here? So these are D2sp3 hybrid orbitals. Okay, so what will happen here? Who is donating electrons? NH3. So now this NH3 ligands, okay, I'm just writing N. Okay, 1 2 3 4 5, there will be one more N. So they will donate electrons here. You have to write it properly. Okay, you have to draw the complete NH3 and you have to show the ligands like this, ligand electrons like this. Okay, so what are the questions asked here now? First one is hybridization. So hybridization is what? D2sp3. Magnetic property. Okay, magnetic property, you can see here there is pairing of electrons, no unpaired electrons are left. So it will be what? It will be a I can say diamagnetic. Okay. Next we have geometry. Okay, geometry, you can see it is octahedral geometry. Octahedral geometry will be there because it is having 6 ligands. Now coming to the next one, CrNH3 whole 6 3+ is paramagnetic, whereas NiCN4 2- is diamagnetic. Explain why. Okay, so CrNH3, if you see, it is a strong field ligand. Okay, so we should expect that there is pairing of electrons and we should have paramagnetic nature, but we should have diamagnetic nature, but it is actually paramagnetic. So what happens here? See, chromium +3. Okay, so chromium electronic configuration in +3 is D3. Okay, so I have D3 configurations like this, 1 2 3. Okay, now if you see, I just need 6 vacant orbitals, right? And for coordination number 6 we have D2sp3 or sp3d2. Now here already 2d empty orbitals available for me, so I don't need to do any pairing here, right? So I can just use this D, then I have 4s and 4p. we need to do pairing in the previous examples to obtain empty orbitals, but here already I have 2 empty orbitals, right? So I'll get D2sp3 hybridization without any problem, without pairing, but I have unpaired electrons left here, so that is why it is paramagnetic. Now if you see the case of NiCN4 2 minus, Ni is what? Plus 2 in this case, so it is 3D8. Okay, 3D8, if you see, I have 1 2 3 4 5, so 1 2 3 4 5 6 7 8. Okay, so here what I have, hybridization dsp2, so I need 1 d orbital, so that is why this pairing takes place and we get an empty orbital here. So this empty orbital we get, that is from 3d, yeah, that is from 3d, and this is from 4s. Okay, dsp2. Okay, so this dsp2 hybridization takes place here. So what I get, this 4 orbitals I am getting here. So now here you see there is no unpaired electron, so that is why it is diamagnetic. Okay, so how can you write this answer in short? So CrNH3 whole 6 3 plus has D2sp3 hybridization with 3 unpaired electrons, so that is why it is paramagnetic. Yeah, so it is paramagnetic. Okay, next we have NiCN4 minus, NiCN4 2 minus has dsp2 hybridization with no unpaired electrons, so that is why it is diamagnetic. Okay, next NiCl4 2 minus is paramagnetic while NiCO4 is diamagnetic, though both are tetrahedral. Again similarly you should be drawing and seeing NiCl4 2 minus. Again Ni is plus 2 and we have 3D8 configuration. So if I just draw here 3D8, okay, 1 2 3 4 5, okay, 6 7 and 8. Now here if you see that since it is a weak field ligand, chlorine is a weak field ligand, there will be no pairing. So for bonding I will have 4s and 4p. Okay, this is sp3 hybridization. Okay, this is sp3 hybridization, 4s to 4p we will get sp3 hybridization. Now what happens here, you see, because it is sp3 hybridization and there is unpaired electron, so this is paramagnetic. Now what is the case of NiCO4? Okay. NiCO4 is having the configuration of there is the nickel charge is 0 here. So what is the electronic configuration? 3D8 and 4s2, right? So 3D8 is there, six, 7 and 8, and we have 4s2 electrons are there. Now what will happen? These 2 electrons will come here. These 2 electrons will come here because of pairing. Why? Because CO is a strong field ligand. And now this 4s is empty and 4p we will have, again there will have sp3 hybridization. So here you see there is no unpaired electron, so that is why it is diamagnetic. Here we have 2 unpaired electrons, so it is paramagnetic. So how do we write this answer? NiCl4 minus has sp3 hybridization and 2 unpaired electrons, whereas NiCO4 also has sp3 hybridization but no unpaired electron, so this is diamagnetic. Okay. Next, okay, so that's all the questions, and here are the list of some important topics that you must revise from this chapter. The first one, very very important, is Werner's theory. Then nomenclature, please practice all the examples given in NCERT. Okay, practice all examples in NCERT, okay, plus in the exercise questions. Next, isomerism, again whatever examples are given in NCERT, only those isomers you should be preparing. VBT for 4 complex, you should know which are the 4 complex. In coordination number 4 you have NiCl4 2 minus and NiCN4 2 minus, okay, and in coordination number 6 we have CO NH3 whole 6 2 plus 3 plus, and we have one more compound, right, CO Cl6 3 plus minus 3, sorry, yeah. So these four compounds, whichever four compounds are given in NCERT, you have to prepare that. Then in CFT, you should be knowing about the d electron configuration. Okay, that is important. Magnetic moment, how to calculate, that you should know. Color, 2 questions I have done in the chapter, those 2 questions you should prepare. And applications, any 3 applications you should remember here. Okay, so that's all, students. If you are able to do this much, then this chapter is done for you. Okay, just a minute. Yeah, so I hope that this video was helpful and you would have revised all the questions. If you have any doubt in any question, please put down in the comment section. I'll definitely address it. Okay, thank you for watching and all the very best for your midterm exams.